Okay, so last time I was talking about principle of least action in field theory, and in particular we saw that the idea that the action should be stationary to lowest order gave us the equation 0 is, gave us the field equations, which were 0 is partial with respect to, let us say, XA of the partial of Lagrange density with respect to the derivative of the field with respect to XA minus the derivative of the field itself. And so this was, this is Lagrange's equation of motion for field theory. If there are several fields, one just puts an index on those several fields like that. And in particular, if the action is a single scalar field, then the equation is grad squared phi minus phi double dot minus m squared phi equals 0, and this is often written as, well, it's written in two different ways. It's written as box minus m squared phi is equal to 0, and I should say it is written as yet another way, which is dA phi minus m squared phi. So there are three ways that this is commonly written, and they all are the Klein-Gordon equations. And see, I'm wondering how much of this other stuff to do. Sometimes an action density, so I may be repeating last time, we don't have a video of it, so not all bad to do that. So sometimes the Lagrange density itself is invariant under a transformation of the fields like this. In other words, sometimes the Lagrange density itself is invariant. One example of that is, for example, in this field here, if you just replace the scalar field derivatives by their Lorentz transforms, not touching the argument x, you just turn the derivatives into how derivatives transform under Lorentz transformations, you then see that this Lagrangian is invariant. It's also true that, for example, the Lagrangian of electrodynamics, which is minus a half f mu nu, this is also invariant under, if you say that a mu prime is L mu nu, a nu, then this thing is invariant. And it's similarly true that the way in which theories are invariant under Lorentz transformations are typically such that the field variables and the derivatives transform in such a way that all those L's cancel and the arguments of the fields change, but that's taken care of because you're integrating over the arguments of the fields with respect to d forth x, which is invariant under Lorentz transformation. So that's one aspect of things. Now, when you have this, you can then say that this is equal to a sum on I. If you apply Lagrange's equations, this tells you that this is dA, this is that times phi I plus partial L partial dA phi I times the change in dA phi I. Now, in many cases, the change in the derivative is the same as the derivative of the change. And so if the change in the derivative is the derivative of the change, then what you have is 0 is a sum on I of dA. I'm sorry, I left out a dA here. I hope that's in the notes. Yeah, it is in the notes. So you have then, you can, as I said, if, as is usually the case, you can change the derivative there, then you can rewrite this as dA of that, and then the whole thing is a derivative. It's the derivative of the sum on I of partial L partial with respect to the derivatives plus times the change. So the change goes here, and when the derivative acts on the second term, you get this. So this is a conserved current equation. 0 is dA JA, where JA is this thing, namely sum on I, partial L, partial dA phi I, times the change in phi I. So this is a conserved current then, and consequently the charge, which is an integral J0 d cubed x, is conserved, at least the charge over all spaces. Well, the change, let us say that the change in the charge in any volume is due to flux of current coming in through the surface that bounds the region. And one example of that is you can set the, suppose you have an ON symmetry, which would then be a sum I equals 1 to n of a half phi I dot squared minus a half grad phi I squared minus a half m squared phi I squared, where here the m doesn't depend on I. Then you have an ON symmetry, and the change in the Lagrangian under, well, I should say what the ON symmetry is. The ON symmetry is that the change in phi I is epsilon times a sum on j, aij, phi j, where aij is minus aji. So these antisymmetric matrices generate orthogonal transformations. And so the change in phi I is this. And so then the charge associated with A is then an integral of the sum on I, and it's the zeroth component of this. And so the zeroth component of this, you see, is the sum on, so let me write that down. It is the partial L with respect to, set A equal to 0, that's phi I dot times the change in phi I d cubed x. And so that is the integral of the sum on I of the conjugate momentum times the charge and change in the field d cubed x. So, and this is a characteristic formula for for a conserved charge. And so this is, in particular, it's the integral of J0 d cubed x. J0 sub A, let us say, d cubed x. And so in particular, this is an integral sum on I, phi I dot Aij phi j, or equivalently pi I Aij, pi I Aij phi j d cubed x, and there's also a d cubed x here. Well, writing is getting a little tight there. Okay, so this is an ON symmetry, and what you can see here, since maybe I'll write it one more time. U sub A is an integral pi I Aij phi j d cubed x, or equivalently, more generally, pi I, the change in phi I d cubed x. And so what you can see is that the charge is the generator of this transformation. So for example, if you have the commutator of the field, phi k, say, of x and t, and you commute that with the charge qa, then you have an integral of the commutator of phi k of x and t. And now this would be pi I of y, and at the same time delta phi I, and the delta phi I is just, doesn't involve any pi's, so it commutes, doesn't involve any pi's, so it commutes with phi. This, by the commutation relations, is an integral delta ij delta cubed of x minus y, and then we have delta phi of y and t d cubed, and this was a y, not an x. And so you see that this is delta ik actually. And so this is the change in phi k of x and t. So you see the charge commuted with that gives you that, and in fact, what I left out here was an I. So the commutator of the charge of the field gives you the change in the field. And the lingo that goes with that is that the charge QA generates the transformation phi goes to phi plus multiply. Okay, well, last time we also showed what something similar, we use a technique similar to this for the case of a space-time translation. And in the case of the space-time transformation, what we have is not that the action density or the Lagrange density is invariant under space-time transformations, but rather that the change in the action density is entirely due to the dependence of the fields and their derivatives on the space-time point. That is to say that the Lagrange density does not have in it the space-time point itself. So in other words, the Lagrange density is invariant under translations in the sense that it only changes because the fields will change. And so this is a sum on I of partial L, partial phi I times partial phi I, partial XA, and then partial L, partial phi I dA phi I, partial let me see, what do I have here? Partial, the second partial of phi, well, let me see if I've got this right. Right. So this is the derivative with respect to A. I'm sorry, I've got this screwed up. It should be right in my notes. Yeah, it is right in the notes. So let me just copy it from the note. It's partial L, partial dB phi I, partial 2 of this with respect to dB, and, well, dB is, yeah, all right, this is okay. So this is, yeah, that's what I actually have written down. And so this is what we've got as how the field transforms. And now we can use Lagrange's equations to substitute for that. And then we can subtract this from the left-hand side. And when we do that, what we get is 0 is sum on I, the Beef derivative, partial with respect to xb, of partial L with respect to the Beef derivative, times the 8th derivative of phi I, plus partial L, partial the Beef derivative of phi I, times the second phi I, partial xb, partial xa, and then minus partial L, partial xa. So I've just essentially repeated that expression there, and now we can rewrite that as dB of sum on I, partial L, partial dB of phi I times partial phi I, partial xa minus delta dA of L. And these notes are online. What I've done is, by the way, with the online notes, is I've combined the notes for chapters 5 and 6 and 7 into one thing, which I just call SW. So it's all together in one PDF. So this is, we can rewrite as the derivative of TEA, where the stress energy tensor, or the energy momentum tensor, then is a sum on I of partial L, this thing here, which is partial L, partial with respect to the XB derivative of phi I times the XA derivative of phi I, and then minus delta BA phi I. So this is the energy momentum tensor, and these components phi I, they could be components of a spinor or a vector field, and won't have the same expression. And so this gives you then the conservation of energy momentum, namely as the integral of T0A dqx. Okay, so any questions? No. All right, so now I'm going to do the case of Lorentz invariance, or Lorentz invariance. And so for Lorentz invariance, what I'm going to remind you of is that in the case of Lorentz invariance, the action is designed so that the derivatives and the field components are multiplied together with constants in such a way that under a Lorentz transformation like this, the Lagrange density is invariant if you ignore the argument x of all the fields. X, of course, goes to x prime under a Lorentz transformation, but if you ignore that, then the Lagrange density is invariant. So that's an invariance of the Lagrange density under a sort of, it's a global transformation that's not really a Lorentz transformation. It's just a, it's just a funny sort of thing that's appropriate, that's useful when you're analyzing Lorentz invariance. So in other words, under an actual Poincare transformation, as we know, a field transforms this way. This is equal then to a sum on L of dl L bar of lambda inverse, and then it's psi L bar of lambda x plus a. So what I'm going to be talking about now is that psi, let's see, we're running out of board space here. Psi L goes to simply dl L bar, and I'll suppress the actual value there, psi L bar like that, ignoring the change in the arguments and suppressing the L inverse. So in other words, what I'm saying is that psi L of x prime is sum on L dl L bar of lambda inverse psi L bar simply of x. So this is a transformation that's not a Lorentz transformation, but is the field part of the Lorentz transformation. And now if we go to the infinitesimal, Lorentz transformation, go to the infinitesimal Lorentz transformation, we've got the change in psi L of x. Again, we're only transforming, we're ignoring the argument, the x part. We're just looking at how the field indices transform. Then this is I over 2 omega AB JAB and the LM matrix element of JAB times psi M of x. So this is the transformation we're talking about, and the change in the derivatives it's I over 2 omega AB JAB LM partial K psi M of x plus a piece that takes into account how the index K will transform, and this is omega Kj partial J psi L of x. So again, this is not really a Lorentz transformation, this is just a transformation under which the action density is invariant in the Lorentz invariant theory, because I'm keeping the x's invariant. This is like the in the case of fermions, we have something like d slash plus m psi. In the case of electrodynamics, or in fact more generally in non-abelian gauge theory, we have a sum on mu nu and a. And this is such that under this kind of Lorentz transformation, or there's a quasi-Lorentz transformation, where we leave the arguments invariant, the Lagrange density itself is invariant, so we can apply Noether's theorem to this. And when we do apply Noether's theorem to it, it gives us this relation. Partial of L with respect to psi L times the change in psi L plus partial L with respect to the kth derivative of psi L times the change in the kth derivative of psi L. And now here, the change in the kth derivative of psi L is not the kth derivative of the change in psi L, because this is how psi L transforms and how the change in the kth derivative is this, and it's not the same as that. And so putting these two together, using these two definitions, what we get is partial L, partial psi L, I over 2 omega AB. So omega AB are the parameters of the infinitesimal Lorentz transformation. Sure. So the omegas are very small. And that is JAB LM psi M plus partial of L with respect to dk psi L. And now, rather a long expression, because we have this term and that term. And so the first term is I over 2 omega AB JAG LM dk psi M plus omega kj dj psi L. Okay, I'm not sure whether, I think I should have raised this L here. All right, now something that I skipped much earlier when talking about the Lorentz group. Let me go back and do it because it's important and I shouldn't have skipped it. We saw that if we were thinking of omega as a matrix, in other words, as L being I plus omega, and by that I meant this was delta AB plus omega AB. So this is our infinitesimal Lorentz, because this is a Lorentz matrix and not the Lagrangian, the action density. But what we saw that is this is a Lorentz transformation, then omega transpose is minus eta omega eta. And it was obvious from that that the space parts of omega were anti-symmetric. And what I want to show you is that the whole thing is anti-symmetric. And so I'm going to rewrite this as omega EA is minus eta AB omega BC eta CE. And then if I multiply both sides by eta DE, I get omega DA equal to eta DE omega EA equal to minus eta AB omega BC eta CE eta DE. And now we're summing over E, so this is just delta CD. Well, we do it this way. This is delta CD. And since that's delta CD, this is minus omega, and the multiplication here brings the beta down to an A there, and this one says that C is equal to D, so that's minus omega AD is equal to omega DA. So this tells us that that if you have the two indices of omega, lower or upper, then omega is anti-symmetric. In fact, whenever you say a matrix, in the context of special relativity, whenever you say a matrix, or general relativity, whenever you say that the matrix is anti-symmetric, or a tensor is anti-symmetric, you're talking about indices that are either both covariant or both contravariant. Okay, so we know then that omega is anti-symmetric. And so we're going to use that in a moment and to rewrite this last bit here. And I seem to be out of board, so I'm going to erase the front board there. Here, you get a handy for manipulating.
And what you were doing back there, were you gearing up to like try and figure out what the conserved charge is that corresponds to?
I'm sorry, give it again now.
What you were doing back here, were you gearing up to start to like try and figure out what the conserved charge is that corresponds to symmetry under the Lorentz group?
Yes.
Okay. What's it gonna be?
Huh?
What's it gonna be? What's it gonna turn out to be?
Well, it's curious. There are, of course, 6 generators of the Lorentz group, and so you expect 6 conserved quantities, and I'm sure that most students, when they hear that, they then are somewhat disappointed that 3 of them are angular momentum.
Yeah.
Okay. And they already knew that angular momentum was conserved. But then, what's even more disappointing is that the other 3 that are conserved are totally boring. It's basically that in empty space, any physical system just moves with a constant speed in a constant direction. So it's conservation of the momentum of the center of mass, I guess.
Oh, really?
Something it's not quite that. It's related to that, though.
Okay.
But on the other hand, what we get is a general expression for angular momentum, which isn't obvious. That is to say, I mean, we know that for ordinary point particles in a freshman physics demonstration, R cross P summed over all the atoms gives you the angular momentum. But for a non-trivial field theory, the angular momentum is something more complicated. And I've never been sure to what extent it's actually been taken into account in all the discussions of spin. For example, people at Rick keep talking about a spin paradox, and I've often wondered, well, is that spin paradox accounted for when you use the real formula for the angular momentum instead of just adding up the fact that the quark spins have one spin 1/2 and there are 3 of them and so on. I brought that up with such people when they were here giving talks, but they never replied. I imagine that they're doing it correctly. They have access to Wilczek, and once you have access to Wilczek, you get things right.
What's Wilczek?
Wilczek, I think he won the Nobel Prize for
Yeah.
asymptotic freedom, and shared it with some other people. Okay, so what we can do, you see, is write this omega k d. I'm changing j to b, first of all. dB of psi L. We can write that as eta ka omega ab dB psi L. And then, taking advantage of the fact that this is symmetric and that's anti-symmetric, we can write this as 1/2 eta Ka omega AB dB psi L, and then minus eta KB omega AB dA psi L. And if we put that in the last expression, what we have is the partial Lagrange density with respect to psi L times I over 2 omega AB JAB LM psi M plus partial L partial dk psi L I over 2 omega omega AB JAB LM. So let me, all right, let me write this formally like that. Partial K psi M, and then plus the last bit, which is this thing up here, 1/2 eta Ka omega AB dB minus eta KB omega AB dA psi L. Okay, so let's remember this all comes from the invariance of the action density under this pseudo Lorentz transformation. And we can combine some of these terms. In particular, we've got an omega AB and an omega AB, omega AB, omega AB. So we can factor out the omega AB, which is arbitrary, and that gives us a matrix equation, namely that 0 is equal to partial L partial psi upper L I over 2 JAB LM psi M. Many of the stuff that much of the stuff that I'm going through today are these steps that Weinberg skipped, but because this is important, I thought I would go over them in the class. I'm not sure whether when he skips something, it's because he thinks it's obvious or thinks it's too hard to LaTeX. On the other hand, he probably has a secretary doing the LaTeX. Okay, so it's that partial K psi M, and then plus a half eta Ka dB minus eta Kb dA psi L. All right, so that's our expression. But now, usually when we go through something like this and we say the Lagrange density is invariant under a certain transformation, and we therefore apply Noether's manipulation to get the answer, to get to conserve current, we replace this by, we use Lagrange's equation, or the field equations, to replace this by a term more like that at the very beginning. Here we've held on and not replaced it yet. So I'm going to replace it now, and so this gives us 0 equals dk of partial L with respect to dk psi L. So that's this thing. And now the whole rest of this, I over 2 JAB LM psi M, and then plus, there's no change here, so I'm just going to write ditto. And so, but you see over here, we've got derivatives with respect to the size everywhere here. And wait, no, I'm sorry. I didn't mean to go that far. I just meant only to go this far. So let's just look at these two terms. These two terms. This is the kth derivative of the partial of L with respect to this. This is the same term, but now we have the partial derivative there. And so we can rewrite this as 0 is equal to partial k of, and now we have partial L with respect to partial k of psi L, I over 2 JAB LM psi m. So that this one term gives us this term plus that term, and then we have this term. And the extra term there is partial L, partial k of psi L times a half, and then this stuff with the etas, eta Ka dB minus eta Kb dA psi L. So that's what we've got at this stage, and we might be a little disappointed because this isn't obviously a conserved current yet. And we can improve it a little bit. We can write it as 0 equals, and again I'm going to use ditto, but in the second term I'm going to rewrite, I'm going to pull out the 1/2, big L squared move there, and then change, I guess, k to a, partial L with respect to the 8th derivative of psi L, partial b, minus partial L, partial b of psi L dA, and I see we have a typo here, so let me just do this, psi lowercase l minus psi lowercase l. Right, it was lowercase l. Okay. So now we've got a 0 is something that looks like a conserved current plus something that's sort of asymmetrical. But in fact, we're on the verge of deriving what's called the Belinfante energy momentum tensor, which is an energy momentum tensor that's symmetric, whereas the energy momentum tensor that we wrote down in general is not symmetric. Yes?
Yeah, I have a question. It requires you to go back just a moment. But
yeah, sure.
If you don't mind. Yeah, I was wondering about whenever we write out the infinitesimal Lorentz transformation, you write delta psi L. Okay, you have this expression. I get that. But then whenever you write delta of the kth derivative of psi.
All right, I've got to figure out where you're talking about, because there's many symbols here.
Yeah, I'll just come up with the point.
Yeah, that's much better.
Yeah. So I was wondering, so for the for the change here, right? You have this term, and you also have this extra term.
Yeah.
I'm wondering what is up with this extra term, and why does it look the way that it does? I mean, I guess that what you're like one term is transformed.
Oh, okay, all right, that's good. That's a good question. Okay, so the first term is ignoring the derivative and just imagining that it's part of the field.
Mm.
But how do derivatives transform under Lorentz transformations? They transform like vector indices, and consequently it's like that.
Okay. Sure.
Okay. That is to say, the Lorentz transformation is this.
You just actually
and just as space components go like this, so too derivatives go like that, apart from a possible minus sign due to eta.
Okay. You don't need to transform it with this, like, I don't know.
Well, we're ignoring the subtle part, namely the arguments of all the fields, because we
Yeah.
want the action density to be invariant under this. This is a pseudo-Lorentz transformation. This is
Okay.
just how the components of the fields and their derivatives
Sure.
transform under a Lorentz transformation, ignoring how the argument x transforms. X, of course, goes to lambda x plus a.
Yeah. Sure.
But when you do lambda x, if you include that, then you've got a more complicated thing, and Lagrange density is no longer invariant. L goes to L of x prime. L of x goes to L of x prime, and so you can't apply the Noether theorem.
Yeah. And I guess the integral that we do in the action density also isn't invariant.
The what?
The integral that we do to get the action density is not invariant? Or
Well,
is
the integral is, yeah, I mean, the
Okay.
theory's Lorentz invariant, and one of
Okay.
the reasons why everything comes out in the wash is that d fourth x prime is equal to d fourth x,
Oh, yeah.
and you
Yeah.
integrate over it. And in
Yeah.
general relativity, there's a square root of g that makes this work.
Yeah. Gotcha.
You get a candy.
Wow.
Okay, so this is our expression, and now, earlier today, we derived the energy momentum tensor, and we can rewrite it by lowering one index, and so TBA then is the sum on I, partial L with respect to dB of psi I. Well, I'm writing it now as psi sub L. Partial psi L, partial XA, minus A to BA L. So that's the energy momentum tensor that we derived with phi I replaced by psi L, essentially. And it has zero divergence, by which we mean dB TBA is equal to 0. Now, this structure that we have here is this first term, which is a total divergence, and then a second term that is this funny anti-symmetric thing. And this funny anti-symmetric thing, you see, is really the part of the energy momentum tensor that can, in some cases, not be symmetric. In other words, in general, this is not equal to TAB. Now this part, of course, is symmetric, the A to AB, but this part isn't always symmetric. And so we can rewrite this equation here as 0 is the kth derivative of partial of L, partial of the action density with respect to the kth derivative of psi L, I over 2 JAB LM psi M, so all this part, and then minus a half TAB minus TBA. And so what Belinfante did was to find a new energy momentum tensor that people traditionally write as capital theta AB, and it's TAB, and it's a rather complicated expression. It's this term, basically, this term written 3 different ways. Minus I over 2, the kth derivative of partial L partial decay psi L J A B L M psi M minus partial L partial psi A of psi L J K B L M psi M minus partial L partial the Beeth derivative of psi L J K A L M psi M. I guess I could have factored out the psi M. Now, there are two important things about this. The first is that the Belinfante tensor is symmetric, and it seems to me this might be a good exercise in Lorentz indices for you guys to do that as a homework problem for maybe next Tuesday, to just show that it's symmetric. So this is, and the reason why one wants it to be, one wants a symmetric energy momentum tensor is that in general relativity, the natural source of the gravitational field is a symmetric tensor, a symmetric energy momentum tensor. And now, could be that we're wrong about that, but most people think that that's the case, and consequently this tensor that Belinfante invented was accepted as being the right energy momentum tensor. Now, there are two important things about the Belinfante energy momentum tensor. The first is that it's symmetric, but the second is that it's as conserved as T is. And so in particular, maybe I'll start the thing here, dA of theta AB, well, this is the eighth derivative of TAB, which of course vanishes. That follows from this. I mean, you can raise the A and there's no problem there. Notice that it's the derivative with respect to the first index that summed, that is zero in the case of the conventional energy momentum tensor. So this one then is that plus, and what I'm going to, well, it's actually minus. It's minus I over 2, and then it's the eighth, so it's minus I over 2 dA dk of something inside the square brackets, and that's this thing, this square brackets. On the other hand, if we look at this thing inside the square brackets, we can see that it's obviously symmetric. Anti-symmetric, sorry. This thing is anti-symmetric in Ka. In other words, this thing is dk of A AKA, which is to say dk minus dk of AAK. Now, why is it anti-symmetric? Well, if you interchange A and K, you get the second term, but there's a minus sign. You go over here, and you interchange A and K, and you've got the generators of the Lorentz group, but they're anti-symmetric. Let me, in fact, I think, remind you of something from our study of Dirac matrices and spin 1/2. Right. Remember that for the case of, in particular, the J's, for the case of Dirac matrices, or a spin 1/2, this was minus I over 4, gamma A, gamma B. So you see it's antisymmetric in A and B. And more generally, it's always antisymmetric in A and B.
Sorry, what about the first term again, though? Not the very first term, the first term after the derivative.
This one?
No, the first term after the derivative.
Oh, well,
Yeah.
the sum of these two are antisymmetric in A and K. And this one is
Yeah.
itself antisymmetric in A and K.
Okay, I see.
So consequently, the divergence of the Belinfante tensor is the vanishing divergence of the conventional energy momentum tensor minus the symmetric derivative of something that's antisymmetric. And so dA theta AB is 0. Okay, so that's a very nice property of, well, it's the key property. No one would care about the Belinfante tensor if it weren't conserved. The fact that it's symmetric, I mean, you can make many things that are symmetric if they're not conserved. I mean, who cares? Where the hell are my notes? Oh, I put them in the chair. Okay, now we can define something called MABC, which is XB theta BC minus XC theta AB. And now what we see is that the eighth derivative of M of ABC, well, this is partial XB, partial XA, theta, I'm going to write this as capital theta, plus partial XC, partial XA, theta AB. Well, this is delta BA, so this is equal to theta AC minus, and this is delta CA, theta CB. This is BA, right, AC minus CB. Wait, I want this to be 0.
XB theta BC. Should it be like?
I must have screwed up here. BC.
The XA theta BC. Since it's not symmetric.
Of course, when the derivative hits these, we get the thing automatically vanishing.
Is the XB theta BC? Is that supposed to be the way it is?
It should be AC.
All right.
XB
Oh,
theta AC.
that's right. This is AC. Obviously, it wouldn't make any sense otherwise. And so this is then BC minus CB, but the thing is symmetric, so this vanishes. Yeah, I should have just followed my notes rather than winging it. So, what do we have? What we have is since this is antisymmetric in BC, we only have six conserved currents. So in other words, JA is M ABC, 0 is dA JA. So we have 6 conserved currents and consequently 6 conserved charges, and in particular the conserved charges are JBC, and they're equal to M0 BC, so we go for the A equals 0 component and integrate over space. That's the charge. And so that's an integral xb theta 0c minus xc theta 0b d cubed x. So these are the generators of angular momentum, and these are conserved. But now, if we look at what they are, then angular momentum is, well, here, let me write down a particular case. In other words, a particular case here is, let us say, Jij is an integral d cubed x of partial L with respect to psi L dot, because we're taking the 0 component here. Xi, the jth derivative of psi L, minus xj, the ith derivative of psi L, minus I, jij Lm psi m. And in particular, this derivative here, in the simplest theories, this thing is just a pi, and the derivative of Lagrangian with respect to the time derivative of a field is just the time derivative of that field, or something simple. But in the case of non-abelian gauge fields, the derivative of the time component of a field is something that is linear, and then another term is, you see, this f squared term is d a plus a squared times dA plus a squared, writing it just in an abbreviated notation. So the derivative with respect to a time derivative is all of this. So this thing here becomes something like a psi dot plus psi psi. So in other words, the angular momentum involves cubic terms when you include the gauge fields of a non-abelian gauge theory. And so that, it seems to me, may lead to interesting terms in the angular momentum when you're talking about strongly interacting particles, hadrons. So you've got these quarks, and the derivatives, the angular momentum involves cubic terms in the gauge fields. Yeah, so we're essentially out of time, and that's most of what I wanted to say. I think that the smart thing to do is to now go more or less directly to QED and do some QED calculation, which are much more relevant to ordinary physics. the, and then after doing some QED, we'll do some path integrals, and then something about not-to-be engaged fields, and I don't know, something about supersymmetry if you want. We have to think about whether we want to have a second semester of this course in the spring. Rich Rand is worried that there won't be enough students to sign up for 524. And so he's tentatively thinking that I'll be teaching math methods in the spring rather than quantum field theory. So if you want to disabuse him of that fact, why don't you send an email to him and me? But you need, I think his actual address is rjr at UNM.edu. Richard J. Rand, I think it's just RJR. And, but you need 5 or 6 people.
Yeah.
Otherwise, he just laughs. On the other hand, what I can do is I can perhaps teach a 1 hour seminar on 6 things and 2 topics. So that's another possibility. Oh, Bernie. All right, so let's